Okay, so what do we conclude about this study of the two plates and the charge in between? So let's make this plate again. The positive plate is here, and on the other side I have a negative plate, not negatively charged. Okay, so if I have a positive charge will have high potential energy on this side. Okay, so here it has high potential energy, and then here it would have low potential energy. Okay, so this is the region for low potential energy for a positive Q. Okay, how about the negative charge? The negative Q, has high potential energy on this side. So this side is the side of high potential energy for the negative charge, and here the negative charge has low potential energy. Okay, so we see that the potential energy depends on which charge we are dealing with. What we are going to do now is we are going to introduce a new concept which is called potential. Okay, so up to now we talked about this potential energy. We talked about electric potential energy. And this electric potential energy depends on which particle we are talking about, positive or negative, and on the position where we put this particle, close to the positively charged plate or negative. Now we are going to introduce a new concept that we call just potential, not potential energy, but just potential. And we are talking about here is electric potential. Okay? And what is the electric potential? The definition is in the next slide. The electric potential is the potential energy divided by Q. Okay? That's the value, the magnitude of the electric potential. And but what we establish by convention is the following. Let's come back to our plate, and let me draw this plate here. Positive plate, negative plate. The convention is on the side of the positive plate, we will say that we have high potential. How we are going to denote potential? With this V. So I'm going to write here high V, high potential, high electric potential. On the side of the negative plate, we are going to say that we have low potential. Okay, so potential energy depends on the charge that we have, depends on the charge that we put here or there between the plates. Potential depends only on the plates. Okay, and we say that the plate that is positively charged has high potential. The plate that has that is negatively charged has low potential. Okay, what does that mean? So let's go to the next slide. What does that mean? It means that our positive charge, so I'm putting here my positive Q, okay, our positive charge moves naturally from high potential to low potential. So let's write this here. Our positive Q moves naturally from high V, high potential, to low potential. How about the negative charge? The negative charge moves naturally. So I'm going to put here my negative charge moves naturally from, now comes the difference. Now the difference moves naturally from low potential to high potential. Okay? The potential energy, be the charge positive or negative, as it's moving naturally, the potential energy decreases. But in terms of potential, this new concept that we're introducing here, positive charge moves from high potential to low potential, and negative charge moves from low potential to high potential. Okay, let's talk more about this thing that we introduced now, electric potential. As you see in this slide, the value of this potential is given by the potential energy divided by Q. Okay, let's talk about units. What is the unit for energy in the international system? Joule. The unit for charge is C. Well, Joule divided by C receives a new name and is called volt. So the unit for potential, electric potential, is volt. We talked about the change in potential energy. Let's now talk about the change in potential. Okay? And let's start the whole story again with the positive charge. So I'm going to start with the positive charge. It's initially in close to the positive plate, so it initially has high potential, and it's going to move towards the plate that is negatively charged, low potential. And this is high. So we are thinking here, we are starting our discussion thinking about a positive charge. Okay, very well. So if I want to write, so my positive charge starts here and it's going to move towards lower potential. So if I want to write the change in potential, I'm going to write it like this: the final potential minus the initial potential. Since we are going towards low potential, I know that this value here will be negative. Okay, using the definition of potential, which is potential energy divided by Q, I'm going to write that this change in potential is equal to the final potential energy minus the initial potential energy divided by Q. Again, this result here is going to be negative. Everything is making sense because the positive charge is moving, is losing. Now, as it moves naturally, it loses potential energy. So this change in potential is negative. Q is positive. We are talking here about a positive charge, so everything is making sense. The whole thing here is again negative. We talked about, we wrote this change in potential energy in terms of work in the previous slide. And we said that this change in potential energy is minus the work divided by, well, in this case, divided by Q. Now, the change in potential energy is minus the work. And since here we are talking about change in potential, we divided by Q. So this is what you're seeing here. This work is positive. So the work is positive. The work done by the electric force is along the direction of the displacement, so it's positive. The charge is also positive, so we are going to get a negative number. Okay, what we said also is that this work for the positive charge, this work is equal to QED divided by Q. We can cancel it, and we have then that this change in potential is equal to ED. Okay, so we got here many different relationships, which are very important. And let me try to extract some of them. One of the things that we got, the final potential minus the initial potential energy, final potential energy minus the initial potential energy is equal to Q final potential minus initial potential. This is one of the equations that we got from all this analysis. Well, another equation that we got is for the work. We said from what we see up there, we see that the work is equal to minus Q final potential minus initial potential. So this is another relationship that we see from here, which is going to show up some slides later. You see, this is the equation that we wrote there. The work done by the electric force following the natural motion of the particle is equal to minus Q final potential minus initial, which is what we have here. What else can we extract from our relationships that we wrote there? Well, we also see that I can write an equation for the electric field in terms of the change in potential. What is the equation for the electric field? Minus the final potential minus the initial divided by D. Okay, So this is another equation which is showing up here in this slide. So you see how many relationships we got for the potential, change in potential energy, work, electric field, all in terms of the change in potential. Okay, some comments that are important here. What is the unit for electric field? In chapter 16, we said that the unit for electric field is Newton per Coulomb. Well, now we are saying that changing in potential, potential is given by volts, and distance is in meters. No? So we can also write, and this is an equivalent way, another way to write the unit for electric field is volts divided by meter. Okay, so this is the equation that we got. Let's have a look at this problem. See, this problem here is asking for the electric field. Let's read. We have two parallel plates are charged to produce a potential difference of 50 volts. If the separation is 0.05 meters, calculate the magnitude of the electric field. Okay. The equation that I wrote here for you, and I'm going to repeat this equation, we wrote it with this minus sign. Okay, so you see this minus sign there, final potential minus initial potential divided by D. But we know that this is an equation for the magnitude of the electric field. Okay, we are not talking about direction here. This is an equation just for the magnitude. And you're seeing this minus sign there, and you may get worried. Well, we are giving the magnitude, and I see this minus sign. But remember, what we are writing here is the final potential minus the initial. For the positive charge, the final potential is lower than the initial potential. So this change in potential here is a negative value. Okay, so we are going to get a positive number, okay, which is going to be the magnitude of the electric field. But when you read this problem here, they don't give you a negative value. They just tell you the potential difference is 50. So they're not worried about, do I have a positive charge? Is it a negative charge? Is it moving to higher potential? Is it moving to lower potential? They don't care about that. They just gave us potential difference. So when they give us potential difference, they usually don't care about what is the direction of the motion. They just give high V minus initial V. Well, minus, so high V minus low V. They just give us a positive value. Okay, in this case of this problem, plus 50. Okay, so if you want to compute the electric field, well, you don't think about putting this minus sign. You just go straight. 50 divided by D, which in that case is 0.05. Okay, because this is an equation that is going to give us just the magnitude, no sign. This is also what happened in one of the problems of the assignment. And if you look at the solution, they are just going to use electric field. Electric field is the difference, the potential difference divided by D. And you see no extra sign there. So this is a much easier way to think about, we are talking about magnitude, so you don't need to worry too much about these signs. Okay? All this issue with the sign is coming up from this first slide because we are thinking about the final potential minus initial for the positive charge, and that's where this negative charge, that's why this negative sign showed up. Okay, in the next slide I'm going to do the same exercise but now for a negative charge. Okay, so let me stop it here.